Bloom filter was a data structure invented by Howard Burton Bloom in 1970. In a nutshell, it's the complement of a cache. Let's talk about what they have in common first. They're both in-memory data structures to speed up queries. Here's the problem. A client has a query against the database, and I'm going to be sufficiently vague here. It could be a relational database, it could be a NoSQL, it could be a web service, it could just be some expensive API. All we need is just something that has a very definite answer, and we want to speed it up. So we insert the Bloom filter and or the cache in between there, and they both get their power from the same strategy that we use in dynamic programming. They have memorization. So they memorize the expensive answers so they don't have to ask them again. So a cache gets its power on a hit. That's how it eliminates a round trip to the database. A Bloom filter gets its power from a miss, and that's how it eliminates its round trip to the database. Here's the value proposition. So with minimal memory, a Bloom filter can tell you in constant time if the database definitely doesn't have your value, and it can do it for an infinite number of missing values. How? Well, we start off with a bit array initialized to all zeros. We're going to insert a value in there, Apple, or rather I should say we're going to insert the markers for Apple. And so we're going to hash mod it like we would with a hash table, get bit positions. We want to do this 3 times, so we're going to have 3 different hashing functions. We'll set bits 45, 2, and 15. We want to do the same thing by inserting the markers for pear and cherry and orange. Unfortunately, orange does have a collision with cherry and orange does have a collision with pear. That's okay, unlike a regular hash table where we would have to go into collision resolution like chaining to buckets or something. We don't care. It's sufficiently robust. We're just going to set the bits whether they needed to be set or not. Here they are. All the bits for the 4 fruits are set. Let's see how we can how this speed up our queries. So if the query is there Apple in the database? We're going to hash mod 3 times, get the same bit positions as before. Since they're all ones, it'll say probably. The same with pear, cherry, and orange. On the other hand, papaya, you're omnipotent. You know that papaya was not put in there. But how does the algorithm do it? Well, it would hash mod it 3 times, get the bit position 17, 15, and 24. Unfortunately, it got 3 collisions. Therefore, it would falsely tell us probably. So yes, false positives are possible. They're rare, but they're possible. Okay, let's look at another example. Banana. Again, you know that banana's not in there. What would the algorithm do with it? It would hash mod it to 1, bit position 1, see that that's a 0, and it actually wouldn't even hash mod it 2 more times because of short circuit logic. If any of the 3 are 0, it can tell us definitely no. And so a Bloom filter has this wonderful property. There are no false negatives. There is a cost to this, and it means that deletes are not allowed. If we go back to our previous example where there was a collision, if you were to delete pear, that is clear its bits, you would be clearing bit 10, and that you would also be clearing bit 10 for orange. In other words, deleting pear would also delete orange, deleting cherry would delete orange, deleting orange would delete pear and cherry. So deletes are not allowed. And there's a cost to all of this. Bloom filter must be pre-populated to be effective, unlike a cache, which can start off empty and just build up as it goes. Here's the rules of thumb to tune a Bloom filter. So if you want to get the rate of positives down to 1 over 100, and I know you're all math savvy, so that's 1%, you would use 3 hashing functions like we did in the previous examples, and you want to give 10 bits per element that you want to store. So as an example, 8 billion values would need a bit array of 80 gigabyte bits, which is 10 gigabytes of memory. and that'll give you your 1% false positive rate. If you want to get that false positive rate even lower, it's certainly possible. The easiest way is just to add more bits. So 15 bits, 20 bits, 25 bits. You could go down to 30 bits and have the false positive rate 1 in a million. For the mathematically inclined, you probably want a formula. So here's the exact probability formula of false positives. I do want to remind you that the phrase exact probability is an oxymoron. But here it is. That's everything that you need to know about Bloom filters.